Next up, we have Dr. Priya J Nadkarni, who will present her recent work on entanglement-assisted Reed-Solomon codes over Qudits. Dr. Priya recently finished her PhD under the guidance of Professor Shayangarani as a member of the PNSIL Lab, Department of Electronic System Engineering, IISc. Her research interest spans across a broad area of quantum information processing and quantum computation, with a focus on quantum error correction codes and their circuit architectures. Over the duration of her doctorate study at IISc, she has published over 12 research works, presented her work in 7 international conferences, and concluded her PhD with a whopping 700-page dissertation. Apart from an active academic career at IISc, she was an active member of the Notebook Tribe and Archery clubs. It's my privilege to invite my mentor, Dr. Priya, for her talk on her work. Dr. Priya, the screen is yours.
Thank you so much, Praveen, for the lovely introduction. I'm audible, right?
Yes, Dr. Priya, you're audible.
Okay, thank you. Yeah, thank you, Professor Shrikant, on providing a very good introduction on quantum computing and information and providing various ways quantum postulates and phenomenon could be used and exploited to achieve quantum advantage. So next, I'll be presenting on a class of quantum error correction codes called as the entanglement-assisted Reed-Solomon codes over Qudits. So this was recently accepted in recently published in Quantum Information Processing Journal. And this is a part of my PhD work with my doctoral advisor, Professor Shayan Srinivasa. This work was funded by MIT through the Vishwesvaraya PhD scheme and also through MHRD. So this would be the outline for my talk for today. First, I'll be mentioning about why do we need quantum error correction codes, one of the major reasons being quantum decoherence. So I'll be explaining quantum decoherence a bit. Then I'll be introducing the quantum state and operator representations that I'll be using in today's talk. Further, I'll be briefly discussing the quantum error correction setup, which is similar to the classical error correction setup, but there are certain differences which I'll be discussing about. And further, I'll be briefly discussing about the stabilizer framework, which is basically a framework to construct quantum codes. And this is similar to the classical additive coding framework, if you are aware of that. And for the qubit case, it's similar to classical linear coding framework. Further, I'll be speaking about a special class of the stabilizer framework, which is the entanglement-assisted CSS coding framework. So this is a framework through which quantum codes can be constructed from any classical linear code. And the main work, I'll then come to the main work, which is basically entanglement-assisted Reed-Solomon codes over Qudits, which is obtained by using classical Reed-Solomon codes along with the entanglement-assisted CSS coding framework. So although the existence of entanglement-assisted Reed-Solomon codes over Qudits are known, a lot of other details were not being explored before by researchers. So in this paper, basically, I have provided the code construction for the code, that is basically obtaining the explicit form of the stabilizers. Further, for a given set of code parameters, I have provided what is the optimal rate code, and also I've constructed a burst error correcting code from entanglement-assisted Reed-Solomon codes over Qudits. And I've also provided the encoding and error correction circuit architectures for the code to implement these codes. And I've shown how it can be implemented in terms of a set of universal quantum gates. So yeah, I'll just start off by providing this illustration of the quantum internet. So the quantum internet has quantum computers connected through quantum and classical communication channels that have classical and quantum repeaters and routers. And these quantum computers are further connected to the quantum satellite through the satellite quantum channel. So for the quantum internet to operate properly, we want all of these devices to work reliably. So we need the quantum computing systems to work reliably, the quantum processors on these systems to work reliably, and the quantum communication, the quantum memory systems, all these need to be working reliably. However, there could be quantum noise which could affect the quantum states in the systems, due to which we cannot process these properly, and hence we need quantum error correction codes. Another major reason is quantum decoherence. So what is quantum decoherence? Quantum decoherence is basically something we can view as follows. That is, let's take we have a quantum system psi, and we have the environment. The environment is also quantum in nature. So over time, the quantum system interacts with the environment and it will get entangled to the environment. So here, entanglement basically means that we cannot represent the quantum state of this quantum system independent of the quantum state of the environment. There is some kind of correlation between them. Although we cannot represent it separately, we can represent it as a mixed state. That is basically an ensemble of states or a probabilistic mixture of exact states or pure states. Now, this entanglement and this mixed state formation actually can be viewed as loss of information from the quantum system into the environment. And this is what we view as quantum noise or a quantum error. And the whole the aim of quantum error correction is basically to obtain back the quantum state psi from this mixed state. So quantum coherence is basically the ability to build quantum mechanical ability of a quantum mechanical system to build interferences, and this is needed if we need to perform quantum computation on quantum information. However, when quantum decoherence takes place, this quantum coherence is lost, and we need to restore back this quantum coherence, and that's why we need quantum error correction codes. Also, the quantum gates themselves could be faulty and they could introduce errors, and we also need to correct those errors. So that is one more reason why we need quantum error correction codes. So my codes are basically for Qudit-based systems, and the main motivation to build codes for Qudit-based systems are as follows. The first thing is that Qudits have larger information content compared to qubits. Also, there's an improvement in the robustness and the key rate of various communication protocols like QKD for Qudits compared to qubits. It is also known that there's an increased sensitivity to eavesdropping and decreased sensitivity into noise for Qudits compared to qubits. And when we use Qudits for simulation of biological and chemical systems, which are basically naturally based on systems which are not two-level systems, but which have more levels, then it leads to richer simulation and emulations. So that's why Qudit-based systems are important. Also, we can design powerful in quantum information processing techniques, and there is a reduction in circuit complexity. However, one caveat would be that the implementation of quantum states and designing decoding algorithms might be difficult for qubits compared to the qubit case. And there's much more research which has been done on the qubit case rather than the qubit case. So with that, I'll be introducing the quantum state and operator representations. So as Professor Shrikant discussed, like in the qubit case, the qubit takes a value not just 0 and 1, but even a superposition. Similarly, for the qubit, it takes a value not just 0, 1, or till q minus 1, where q is the dimension of a qubit, but it can take a superposition of these states. So in this superposition, the coefficient is basically a complex value, and the state is a normalized state. So that's why, because the state can be uniquely represented with respect to these AIs, hence we just represent it by a q-dimensional vector in the complex space, which is a normalized vector. On performing measurements, similar to the qubit case, here also the quantum state collapses to one of the basis states. And the qubit can be implemented using superconducting devices, ion traps, quantum dots, photonics, and various other technologies. So I'll be speaking about quantum error correction codes, which basically deals with finite fields, and hence I'll be representing these basis states in terms of a finite field element. So when we consider finite fields are the size of a finite field is always a power of a prime. Hence we'll be considering the dimension of the qubit to be a power of a prime. And let's consider a finite field element beta. This is the polynomial, the expansion of the element beta and the polynomial basis. So the state is obtained by basically considering this polynomial expansion by replacing the alphas with p's, and whatever value we get, that will be the value of b, which belongs between 0 and q minus 1. And hence we assign this beta to this b and obtain the state representation. Further, for the operator representation, we consider the field trace of an element. So field trace of an element is an FP linear function, which is given by this expression over here. As quantum dynamics is linear, and because there's a normalization constraint on the state, as I explained in the previous slide, the quantum operators are unitary in nature. So we had this complex space of matrices because we were dealing with vectors, and now we have this unitary group where all our operators lie. So now Yeah, so now this particular unitary group has infinite number of elements, and because we want to deal with them, we consider a unitary basis for this particular space of matrices, which is GPK here, which is a subset of this unitary group. So I think many of you would have heard about the poly basis. So for the qubit case, the unitary basis is a poly basis, and for the Qudit case, we'll be considering this basis, which is similar to the poly basis. That is, here also it's a multiplication of x and z operators, where x and z are defined as provided here. And these can be further represented in terms of just a two-dimensional vector, where the first element corresponds to the beta in this x operator, and the second element corresponds to the gamma in the z operator. And this is known as the field isomorphic equivalent of this operator. Further, for state and operator representation for n qubits, basically for the basis, is obtained as the tensor product of the individual state and operator representation for each of those qubits. So even for the field isomorphism, we just have a 2n dimensional vector here, where the first n components correspond to the x operator and the next n components correspond to the z operator. So next, let me take you through the basics of quantum error correction codes. So the main aim of quantum error correction is to incorporate redundancy in the quantum information, such that when an error occurs, we can exploit that redundancy to retrieve back the information and correct the code word. So the quantum error correction setup is similar to the classical case. That is, we have a message here. It's a quantum message. We encode it. We get a code word, and we have an error. This time it's a multiplicative error, not an additive error like the classical case. And then we perform error correction. So here again, we have syndrome computation, we have error detection, and then error recovery. And further, once we recover that, we get a a code word estimate, which we can decode to get a message estimate. And if E is a correctable error, the message estimate is equal to the message. And the quantum channel in this case could be a depolarizing channel or an erasure channel or various other channels. We have considered a quantum depolarizing channel for our EARS codes. So here, with the probability of 1 minus s, there is no change in the state, while with there are all the other basis errors occur with equal probability. So why can't we use classical error correction codes for quantum error correction? It's basically because of these three main challenges. First is that measurement destroys superposition. Second is the no cloning theorem, which Professor Shrikant explained. And also because errors are continuous. We are not just dealing with the bit errors or the symbol errors, but here we'll be dealing with the bit flip errors and the phase flip errors. Or in the Qudit case, we have the X errors, Z errors, and the linear combinations as well. So all these challenges were overcome by Peter Shor, who proposed the 1-qubit error correction code in 1995, and further in 1996, Daniel Gottesman proposed a framework for quantum error correction codes. This was for the qubit case. So the stabilizer framework, which Daniel Gottesman proposed, was basically similar to the classical additive codes. That is, for the qubit case, it's nothing but the classical linear codes. So here, let me just explain what is the analogy. So in the classical case, we have a parity check matrix, which basically, we have a parity check matrix associated or completely defining the classical linear code. When we have a received vector, which is erroneous, which comes in, we check the orthogonality of the received vector with each row of the parity check matrix. And based on that orthogonality or the inner product, we form the syndrome. And based on this syndrome, we can deduce the error and correct the error. So similarly, in the quantum case, this quantum mechanics postulate was used. That is, in any measurement, only the eigenvalues of the quantum observable can be observed. As Professor Shrikant discussed before about the poly group, the polys actually either commute or anti-commute. So therefore, these eigenvalues are either 1 or minus 1 when we operate an error E on something like SI size. So ESI could either be ESI could be either be SIE or minus SIE. So exploiting that and exploiting the quantum concept of stabilizers, which is basically that stabilizers an operator but does not change the state, that is SI psi equals to psi. What was done is that the eigenvalue of each of when the SIs were operated on E size, the eigenvalues were computed, that is eigenvalue of SI with respect to E psi, and these were made to form the syndrome, and based on this, the error was deduced and it was corrected. So here also we have a concept of the check matrix, which is similar to the parity check matrix, but here we kind of take the isomorphic equivalence of the stabilizers and stack it one above the other to form the check matrix. So just summarizing the stabilizer code, basically we have a state space, we have an operator space, we consider an abelian subgroup of this operator space, which is the stabilizer group, and the code word is basically obtained as the set of all states which are stabilized by all operators in this group. And these are the code parameters that I have provided here. So like in the classical case, the design of the code is basically equivalent to designing the parity check matrix. In the quantum case, the design of the stabilizer code is equivalent to the design of the check matrix hedges. So this check matrix hedges, because this is 2n in length, and here say we have some row number of rows, hence it's this is equivalent to a classical additive code, because each of these yeah, so this is equivalent to a classical additive code. I won't go into the details of this, but yeah, this is equivalent to the parity check matrix of a classical additive code that satisfies this dual containing criteria. That is, it's a self dual code, sorry, a dual containing code where the inner product considered is the trace symplectic inner product. So hence, if you want to design a stabilizer code, we need to design the corresponding additive code. So now, instead of classical additive codes, classical linear codes are majorly studied in the classical world. So the Kaldemang-Schwarz-Stein coding framework provides a method to construct quantum codes from classical linear codes. So the method is as follows. We consider two codes C1 and C2 that satisfy this dual containing criteria. That is H1, H2 transpose, the parity check, the product of their parity check matrices is equal to 0. And further, we obtain a CSS code by considering this following parity check matrix for the code and using the stabilizer framework. So the for the qubit case, the check matrix is nothing but in a diagonal form. That is, it's in the form H1, 0, 0, H2. This is for the qubit case. And this is one of the contributions in this paper. Further, like here we are considering this dual containing criteria, but it's not always possible that every two codes satisfy this dual containing criteria. So how do we construct quantum codes from codes that do not satisfy this dual containing criteria? So Todbrun and their group, they had an idea, and they proposed that what we could do is, suppose we consider two codes that do not satisfy this dual containing criteria, then we can extend them. That is, we extend H1 and H2 using a few symbols, say any symbols over here, to extended codes, and these extended codes would satisfy the dual containing criteria. And then we use the CSS framework to construct the code. So our main contribution over here is that we showed that the minimum number of qubits needed for this extension is nothing but rank of H1, H2 transpose. So this was for the qubit case. For the qubit case, Professor Mark Weil has provided this particular expression, which is very similar. And in this extension, the properties of the code, or the distance properties of the code, we wanted that it has to be dependent on these classical codes. Hence, whatever bits are used for extension or symbol is used for extension, the qubits that correspond to them are assumed to be maintained error-free at the receiver end, and these qubits are assumed to be entangled to the qubits at the transmitter end. So using this framework and with Reed-Solomon codes, I'd be constructing my codes. So first, let's have a briefly discussion into classical Reed-Solomon codes. So classical Reed-Solomon codes, they're efficient codes that was proposed by Reed and Solomon in 1960, and the parity check matrix of the code has been provided here. The length of the code is p power k-1 is what I'm considering here. So I'll be going into the parity check matrix a bit more in the next slide. So what are the advantages of these codes is that they have a guaranteed burst error correction capability, or rather their binary expansion has a guaranteed burst error correction capability, due to which they're widely used in classical transmission and data storage systems. The classical Reed-Solomon codes, they saturate the classical singleton bound. So hence they're very efficient codes. And also because of that, they're algebraic codes, they have an algebraic structure, which means that there are efficient encoding and decoding circuits. So coming to the parity check matrix of this code, So let's consider this Van der Monde matrix. This is a type of Van der Monde matrix. So this is an n by n linear transform which is invertible. So the parity check matrix is obtained by considering if we want a code of minimum distance dm minus 1, then the parity check matrix is obtained by considering dm minus 1 rows of the Van der Monde matrix, consecutive rows of the Van der Monde matrix. And the Van der Monde matrix used over here, it is basically used even to obtain the finite field Fourier transform, because as I mentioned, it's a invertible matrix. Hence, using this finite field Fourier transform, we can basically transform a vector from the time domain to another transform domain. So when we kind of apply this finite field Fourier transform on a code word of a RS code, we obtain that d minus 1 elements of this particular transform domain vector are zeros, and this we call as the spectral nulls of the code. And we get these zeros because the parity check matrix is basically is a submatrix of the Van der Monde matrix. So further, we use that finite field Fourier transform to encode the code and also in syndrome computation. So the encoding is basically introducing zeros in the spectral nulls and introducing the message in the rest of the places and applying the inverse of the finite field Fourier transform to get the code word. And error correction involves applying the finite field Fourier transform, and the syndrome is obtained wherever the spectral nulls positions are. And further from the syndrome, error detection is performed using Berlekamp-Massey algorithm, Euclidean algorithm, and others, and the error is obtained. And based on the error, the inverse error is applied and it's corrected. So I just presented this because even for the quantum case, it's going to be similar. So please keep it in mind. The next is basically the problem of construction of quantum Reed-Solomon codes from classical Reed-Solomon codes, and about how to design their quantum coding architectures. And we feel that this problem is important because the quantum Reed-Solomon codes, they could be used in quantum memories as well as quantum communication channels. So the prior work in this area is that Gressel et al., they have proposed the quantum Reed-Solomon codes over qubits from dual containing Reed-Solomon codes over f2 power m or 2 power k, and they have provided their quantum coding architectures for the same. But this is for the qubit case. Garadia et al., they have proposed quantum Reed-Solomon codes for qubits from dual containing Reed-Solomon codes. However, they have not provided the quantum coding architecture. For the quantum entanglement-assisted Reed-Solomon codes, the existence of these codes have been shown before. That is, it's basically a direct application of using the entanglement-assisted CSS coding framework along with the Reed-Solomon code. But no one has proposed the code construction or the coding architecture before. So that's what our work is about, that we have provided the code construction of the entanglement-assisted RS codes over Qudits. That is, we have considered these two RS codes, which have parity check matrices at V1 and HV2, and we are providing the entanglement-assisted RS code. We have shown that this code is non-degenerate and saturates the quantum singleton bound. We have provided the optimal rate code, we have provided a burst error correction code, and also provided the coding architectures in terms of the universal quantum gates. So let's first look into what was actually known before. So what was known before is, suppose we consider these two classical RS codes with parity check matrices HB1 and HB2, then an entanglement-assisted RS code with these parameters could be obtained. And here the expression for NE, which is the minimum number of entangled qubits needed, or pre-shared entanglement qubits needed, was known to be rank of HB1, HB2 transpose. What we solved further is that we provided an analytical expression for this NE that does not involve rank analysis, but is linear in terms of the code parameters. We also showed that the code is a non-degenerate code and saturates the quantum singleton bound. And we provided efficient method to obtain the set of stabilizers from HB1 and HB2. We also provided an optimal rate EARS code. So we provided an analytical expression for NE, which is basically the expression provided here. So the idea to obtain this expression was as follows. As you can see, we have 4 cases. So I'll explain why we need these 4 cases. NE is basically rank of HB1, HB2 transpose. So when we analyze the inner product of rows of HB1 and HB2, what we realized that when we consider the inner product of ith and jth rows, we obtain that when v plus I plus j mod n is not equal to 0, the value of this inner product is 0, while in the rest of the cases, it's equal to p minus 1. When we analyze further, we realize that for any particular I, there's at most one j for which this inner product is not equal to 0. And similarly, for any particular j, there is at most one I for which the inner product is not equal to 0. So thus we could obtain distinct non-orthogonal pairs. That is basically non-orthogonal rows of we could obtain distinct pairs of non-orthogonal rows. And one more observation what we did is that the range of I and j is basically from I to dm minus 1. So I plus j is between 1 and 2 dm minus 1. So when we say that v plus I plus j mod n equals to 0, it basically means that v plus I plus j is a product of n. So it can be n or 2n or 3n. So we further divided it into cases. So when v plus I plus j, the maximum value of v plus I plus j is v plus 2 into dm minus 1. So when v plus, this should be dm. So when v plus 2 dm is less than n, then this sum can never be equal to n, or this condition cannot be satisfied. And hence for the first case, the number of entangled qubits needed is 0. For the second case, the sum was basically between n and 2n, and we further divided this into two more cases based on the value of dm, because when we add the minimum of I and the maximum of j, that is 1 plus dm minus 1, we get dm. So based on that, we got two more cases, and the third case was basically when this particular sum was between n and 2n, and hence 2n and 3n, and hence considering these three cases, we obtained this expression. So further, we showed that the code is a non-degenerate code. Non-degenerate code basically means that there are no two correctable errors that transform the code word to the same state. Non-degenerate, this result is important because the properties of non-degenerate codes are well known, and also the coding bounds are known for non-degenerate codes. And we further showed that this entanglement-assisted RS code saturates the quantum singleton bound, and it's an efficient code. This non-degenerate code result actually helped a lot, because recently it was shown that degenerate quantum codes need not even satisfy the quantum singleton bound. Further, we provided the optimal rate entanglement-assisted RS codes, where we basically showed that when we consider n and dm to be constant, by just changing b1 and b2, we could change the rate of the code, and the optimal rate is obtained when b1 plus b2 equals to n minus dm plus 2. So the next problem which we solved was on the code construction of entanglement-assisted Reed-Solomon codes over Qudits. So basically, we have HB1 and HB2, and now we need to expand this HB1 and HB2 to HB1 MB1 and HB2 MB2, so that they satisfy the dual containing criteria. The particular codes satisfy the dual containing criteria. So to obtain that, what we did is we first obtained the non-orthogonal pairs between HB1 and HB2. As I mentioned before, using this property, there are non-orthogonal pairs which are distinct from each other. So the idea to extend HB1 using MB1 was that to each non-orthogonal pair, we assigned one particular qubit or one particular symbol. And because here the inner product is P minus 1, on the particular assigned symbol of qubit, the expansion was such that the inner product between them were 1. So basically, we on the extended symbol, we had 1 and 1, so that the inner product is 1, and that 1 cancelled out with this P minus 1 to make the extended rows to be orthogonal, or the codes to satisfy the dual containing criteria. So the procedure has been given in this theorem, where basically we have the non-orthogonal sets based on which were the non-orthogonal rows and orthogonal sets, and the non-orthogonal sets have been extended by ES transpose over here, which basically corresponds to the ones, and the orthogonal sets have been extended with zeros because they're already orthogonal. This is an example which I'll be skipping. Then further, for the burst error correction of the code, in one of the previous works, what we have shown is that the basis state and operators of qubits of dimension p power k can be expressed as a tensor product of k basis state and operators of qubits of dimension p, due to which we can view one qubit to logically contain k subqubits. So using this basis state and operator, we obtain the burst error correction code. So the idea was as follows. So we have the check matrix of the code. So what we did is that using the basis operator representations or decompositions that I mentioned before, we expanded this check matrix to the check matrix HSP. So if this was a 2n by a row by 2n matrix, this would be a row by 2kn matrix. And considering this as a check matrix of the code over qubits of dimension p, we obtained a burst error correction code, which has the same burst error correction capability as the classical codes, as the binary expansion of the classical Reed-Solomon codes that are currently used in the classical memory devices and communication systems. So further about the encoding. So this was the encoding for the classical RS codes, and this was the error correction mechanism. So what are those for the quantum codes? So we obtained very similar results for the quantum codes as well. But before that, I would just introduce a few state and operator representations. So for the state operator representations, we'll be considering the DFT transform. The DFT transform is basically a transform that converts the X operators to the Z operators upon conjugation and vice versa. Then we have the add operator, which basically adds the basis states. Like here we have theta 1, theta 1, theta 1, theta 2, but the result would be theta 1 plus theta 2. And we'll also be considering two more states, which is basically a single qubit state epsilon, which is equal to the DFTP inverse acted upon on 0. So the X operator stabilizes this state. And also we'll be considering a 2 qubit entangled state eta, which we'll be using to encode. And this would be the state which exists between the receiver end and the transmitter end. So the encoding procedure which we obtained was as follows. So here QFFT is the quantum version of the finite field Fourier transform. So to obtain the encoding procedure, these two relations were considered. So here, these are the stabilizers of the code, or just the initial operators. And then on applying quantum version of the finite field Fourier transform, or the inverse of it, on applying the quantum version of the finite field Fourier transform, we obtain X operating on n minus f plus 1 qubit and Z operating on f plus 1 qubit. So because of this conversion, what we obtain is the spectral nulls to be the X spectral null, we obtain it as n minus b1 minus dm plus 3 and so on till n minus b1 plus 1. This is because this is obtained by substituting f here with b1 to b1 minus dm, b1 plus dm minus 2, which is basically obtained from the stabilizers or the parity check matrices of the RS code. Similarly for z, by substituting f by b2 to b2 plus dm minus 2, we obtain the z spectral nulls. So these are basically the positions of the spectral nulls in the block of the code. So here, if we consider this block is basically having n plus ne qubits. So we can divide this code word block into multiple sub blocks over here. So here we have BT. BT is basically the overlap of X and Z spectral nulls. So which is where we introduce the entangled qubits. So this is BT. It comes between BZ and BX. And then we have the BZ, which is basically the leftover Z null spectrum. And then we have BX, which is the leftover X null spectrum. And then we have BM, the leftover qubits, which is BM, where we introduce the message qubits. And at the receiver end, whatever is there, we introduce the entangled qubits again there. So the entangled qubits come between BT and BR. So based on this, we have a very simple encoding circuit that we have proposed. So in BM, we introduce the message. In BZ, we introduce the state 0. In BX, we introduce the state 0 operated upon by DFTP inverse. This is because DFTP inverse 0 actually is stabilized by X, by the operator X. And then in BT and BR, we introduce the entangled state, and we inverse of the finite field Fourier transform operator to obtain the code word. So the encoding only takes place at the transmitter end and not at the receiver end. And that is the encoding procedure for the code. Further, for the syndrome computation procedure, we have the basis error over here. The syndrome is computed so as follows. So here, because it's a CSS code, the X and Z syndromes are separable. So here XZ is equal to beta into HB2 transpose, because the Z stabilizers correct the X error and the X stabilizers correct the Z error or deduce the Z error. So similarly we have for the syndrome based on the Z error. So the syndrome computation is as follows. We apply the quantum version of the finite field Fourier transform, and then we perform operations where the computation of Sx involves information in the Z spectral nulls. Like for example, for Sx, we are using the information from Bz, Bt, and Br. And for Sz, we are using information from the spectral null, which is basically from Bx, Bt, and Bt. So based on this particular syndrome computation architecture, we compute the syndrome, and further the syndrome is measured and passed on to the classical Berlekamp Massey algorithm or the Euclidean algorithm, where the error is deduced and the inverse error is applied to obtain back the code word. And further, like in the circuits which was provided, only the quantum version of the finite field Fourier transform was not a 1 or 2 qubit gate. It was known that the universal set of quantum gates for qubits is basically all single qubit gates along with the AND gate. And hence, to obtain the circuits in terms of universal quantum gates, we need to decompose this quantum version of the finite field Fourier transform and its inverse in terms of 1 and 2 qubit gates. So this is achieved by and we have provided results for this. That is, first we have provided how quantum version of a permutation matrix can be obtained, how the quantum version of an invertible linear transformation can be obtained, and how quantum version of finite field Fourier transform can be obtained further in terms of 1 and 2 qubit gates, and the complexity of it is O of n squared. So I would like to conclude my talk by saying that quantum coherence is necessary to perform quantum computation and processing, and quantum error correction codes are needed for large-scale quantum computing devices. The main contributions of my work was to basically provide a procedure to obtain the explicit form of the stabilizer codes for the entanglement-assisted resolvement codes. And we also provided an analytical expression for the minimum number of entangled qubits. We studied various properties of the code, provided an optimal rate code, provided a burst error correcting code, and provided the quantum coding architectures in terms of a universal set of quantum gates. The future work in this research area would basically be implementation of these codes. So yeah, I thank all of you for attending this talk. If you have any questions, I would be happy to answer. Thank you.
Thank you, Priya, for your interesting talk and your research. We'll take any questions. Looks like there are no questions. Dr. Priya, I'd like to thank you again for your talk and wish you the very best for your future research. On behalf of IEEE-IISc Council, I kindly accept this virtual memento from our end as a token of our appreciation for taking time to deliver a wonderful talk on your talk.
Yeah. Thank you, Praveen. Thank you, Kamsa.